In this video, we will be talking about polymorphism in C++. The word polymorphism means having many forms. Typically, polymorphism occurs when there is a hierarchy of classes and they are related by inheritance. C++ polymorphism means that a call to a member function will cause a different function to be executed depending on the type of object that invokes the function. Think about this example. If we have different objects and we call the same function on all of those, like speak, they create different responses. And this is exactly what polymorphism is. So let's say in these four cases, you will just call the function speak, and your humans are going to respond with say what. The cat, the dog, and the rooster are going to respond in identically different ways of response. And this basically is the polymorphism. To understand this better, let's take a look at the piece of code and go from there. Let's see, what do we have here? So we have a class named shape, which in this class shape, we have two protected members, width and height. We have the public constructor, which has both A and B coming in to set width and height. And then we have a method called area, which basically puts out parent class area. And the reason that we have it in here is because in the output, we want to make sure if this is the area function of the parent called or of the child called. Then down here, we create a class rectangle, which publicly inherits from class shape. And then we have a rectangle constructor over here, okay, which as you can see is also inheriting from the constructor of shape. And we have an integer area. Notice that this method over here has the exact same signature as this one up here in the shape. But this time, in the cout, we have a different message which says rectangle class area. So again, over here, we have integer area defined. And down here, we have integer area defined in a different way. So in this case, it doesn't do anything but to print out the message. But down here, as you can see, it gives us the message, plus it actually returns width and height. Then we have class triangle, another class, which is again inherited from the shape in a public manner. And then you have another constructor here, which inherits from shape. And then another integer area. This time it says triangle class area and does a different calculation. So the goal here was to create three different area methods in three different classes that they actually are acting different. Thinking about example, here it says say what, here it says moo, and here it says woof woof. Now in the main, I'm creating an object shape as a pointer, and then another object of rectangle, setting it up, another object of triangle, and setting it up. So now I have shape, which is a pointer, rectangle and triangle, which are the objects of the classes. And then I store the address of rectangle in the shape, so as you can see down here, and then I'll call the area on the rectangle, okay? And then I store the address of triangle in the shape, and then I call it, again, call the area on the triangle. So what do you expect to see over here? So let me just do this a little bit so we have more room to show stuff at the same time. Okay, and I'm gonna run this program. Successfully built, and look what's going on. So in both of the function calls, you see it says the parent class area, which means whether we did it this way on the shape which had the triangle address or had a rectangle address in all the two calls, it goes all the way back here and calls this function. So basically, this area function and this area function, which are from the respective classes to rectangle and triangle, never were called. The reason for the incorrect output is that the call of the function area is being set once by the compiler as the version defined in the base class. This is called static resolution of the function call. Static linkage, the function call is fixed before the program is executed. So in a static resolution or static linkage that you can see is happening right now in this code, basically the function call is fixed before even you run the program. So that's going to be fixed in the compile time. This also sometimes is called early binding because the area function is set during the compilation of the program. So now let's make a slight modification in our program and proceed the declaration of area in the shape class with the keyword virtual. Okay, so let me change it and see how it is going to be. So I'm going to come up here to my shape, and then here when I'm defining the integer area, I'll just set a keyword here called virtual. Okay, now virtual integer area is up over there. After this slight modification, let's run it and execute it again. And now as you can see, it changed. Now right down here, and let me just go back here. So when we call the shape area on rectangle, the rectangle class area actually is being executed. And then when we do the shape on the triangle, as you remember, that's an address to the triangle object. Now the triangle class area is being called. And all these happened just through turning this guy from being integer area to virtual integer area. Let me just remove this for a second, run it again so you guys remember what was the result before. So without virtual, as you can see, parent class area is going to be called no matter how you call it. And then if I make it virtual, then you're going to have the respective classes to the objects. So basically when we call the area on the shape, which in this case is a rectangle, the rectangle one is going to work. So when I'm calling it on the cat, the moo is going to work. And then when I'm going to call it on the dog, the woof is going to work. So pretty simple as that. As you can see, each of the child classes has a separate implementation of the function area, which we looked at it up here before. Okay, this is how polymorphism is generally used. You have different classes with a function of the same name and even the same parameters, but with different implementations. So let's go back to the slides and review virtual functions. A virtual function is a function in a base class that is declared using the keyword virtual, as you noticed up here. This is a virtual function. Defining in a base class a virtual function with another version in a derived class signals to the compiler that we don't want static linkage as we discussed for this function. What we do want is the selection of the function to be called at any given point in the program to be based on the kind of the object for which it is called. This sort of operation is referred to as dynamic linkage or late binding. So let's go back to the code again pretty quick. So when I put this virtual out, if this guy doesn't exist, just ignore it, then I have a static or early binding, which in this case, the area function here is the only and only one which is going to be called at all situations. When I put virtual here, now I have the dynamic binding, and what this virtual is telling the compiler is, okay, I'm virtual here, which means only call me if the object you're dealing with is of shape type. If it is on my child types, go there, figure out their area function, and call that area function respectively. So as you can see, the polymorphism can happen in two steps. First, make sure you have the exact same definition of the function with the signature in all the childs, and then make the one in the parent to be virtual, and then you are almost good to go. So it is possible that you want to include a virtual function in a base class so that it may be redefined in a derived class to suit the object of that class, but that there is no meaningful definition you could give the function in the base class, which is awesome, which means in this case, if we go back to the code and we want to have a pure virtual function, it means in this case, there should not be nothing happening in this virtual function. So let me just create this and turn this shape to a pure virtual function. So I'm going to get rid of this line. I don't need this anymore, okay? And the only thing, I don't even need a return in this case because this is going to be pure virtual, right? So no return value for pure virtual. Simply say virtual integer area, and for the sake of just setting it to something, I'll set it to 0, which means I don't need this guy anymore, and I don't need this guy anymore. So now, as you can see with just this one line, I have a pure virtual function. And the 0 equals 0 tells the compiler that the function has no body, and above virtual function will be called pure virtual function. Again, get rid of all the implementation, hold on to the virtual, and then make it equal to 0 just to tell the compiler that, hey, there is no body for this function. If you don't put the 0 over there, then the compiler is waiting for a definition. Remember when we were defining the classes and in the interface.hpp part of the class, we were putting a function name and then later we were implementing that in CPP? This equals 0 tells the compiler, hey, there is not going to be no further implementation for this virtual function, and therefore this is going to be a pure virtual function. Let me run this so that you can see it in action, and as you can see, it works absolutely properly. And this basically concludes our work and video on the polymorphism. Of course, you need to practice to get perfect in this, but you got the concept in this video. Thank you.